Good evening, everybody. It's lovely to see you here. I hope you've had a lovely day. For those of you who are new to us, I'm Alan Willison. I'm the chairman of the Hertford Astronomy Group, and we've got a really super evening for you tonight. Just before we get started, our usual housekeeping rules, the fire alarm, if it goes off, please exit each side, gather on the car park, and we'll check everybody is safe. If you need the toilets, they're just outside the door, and on the way in you'll see them on the left-hand side. For those of you on Zoom, it's lovely to see you as well. I know we've got people, I think, from Norfolk and possibly Bristol as well tonight, so a very big welcome to you. Can I just ask, can you keep your hands away from the space bar? Otherwise you might join in the conversation. For those of us in the auditorium, can I ask if you've got mobile phones or any other devices with displays or make noises, can you please turn them off so they don't distract other people? So the format for this evening is we are so privileged that we've got 3 students from the University of Hertfordshire who are going to give us 3 really super talks. They've only been at the university since September, so you can imagine that if you have got any nerves, we well understand. So I'd like to get the meeting off to a start by introducing our first speaker, and it's Camilla. So please give Camilla a very big warm welcome.
Welcome everyone. My name is Camilla. I'm from Italy, from Trieste, or from Venice, if you have never heard of Trieste. I did my bachelor in Trieste, and then I moved to Germany, to Cologne, to do my master, and then I came here for the PhD. So this evening I will talk to you about the most powerful engine in the universe, which are black holes, like a small spoiler, and also what they have to do with star formation. But let's start from our universe. As you can see from this picture, taken from one of our most recent observatories, like the Vera Rubin telescope, there are like many galaxies and stars in our universe. But like how do our universe come out to be so big and so rich of galaxies? It all started with the Big Bang. After a Big Bang, there was a very rapid expansion, and after that, however, there was a period called the Dark Ages. So at this time, the universe was mostly neutrals. There was like no protons and electrons flowing around. They were all nicely neutral atoms. And because of that, there was no source of emitting light. It was all dark. And we have to wait until about 180 million years after the Big Bang to see the first stars appearing. And this period is called cosmic dawn. So, but one may ask, how do stars form, like in general? So you know that we have clouds in our sky. Like similarly, also in space, we have clouds. These clouds in space, they're made of gas and on smaller amount of dust. This is not the dust that we have on our homes. They are like small particle with a carbon or a silicate cores of a micrometer size. And we'll come back to the dust at the end. But mostly it's about gas. And in this gas is mostly made of molecular hydrogen. That's why they're called molecular clouds. This is one of the clouds in our galaxy, the Milky Way. These are called the pillars of creation. and they're basically the nurseries of new stars. Like, how does it work that from a gas cloud then we have stars? In simple terms, these clouds, they're very dense and cold, so the atoms can come very close to each other, and they like to stay with each other, so they go further to collapse, so they come even closer to each other until the temperature is so high that we have a newly born star. This picture was taken by the Hubble Space Telescope, which was our powerhouse from the 90s. We had so much fun with the Hubble Space Telescope, but like nowadays, the new big thing, you may have heard about the James Webb Space Telescope. And in this image, you can appreciate how much more details we can see of these clouds with this new space telescope. And also we'll get back to the James Webb telescope towards the end. So we know how stars are formed, but we astronomers, we asked ourselves if the star formation in the history of the universe was always constant or not. So we measured that, and this is a plot I will walk you through. So on the horizontal axis, you have the look-back time in billion years. So here at 0, it's like our present, and at about 13.8 billion years ago, it's where the Big Bang started. On the vertical axis, we have the amount of new stars being formed in a certain time and in a certain volume. So the rate of new stars being formed. So if we start from the Big Bang, from the right, we see that the amount of stars being formed, it increases until it reaches a peak about 10 billion years ago. And after this peak, then it decreases again. So this is very peculiar. We don't know exactly why this is, and so we want to know more about it. And this peak of star formation activity, so-called, it's called the cosmic noon. So in our timeline, from the beginning of the universe, like we have the cosmic dawn, then we have this cosmic noon where the star formation peaked, and then the stars and the galaxies, they continue to evolve and expand until we arrive at our present day, at the universe as we know of at the moment. Because the light, it travels at the constant speed of 300,000 kilometers per second. So I had to say that so the information that we have of the universe, it comes mostly from the light emitted by these different galaxies and stars. So with our telescope, the furthest away we observed a galaxy, the more old the galaxy is. So basically, we're seeing in the past. So we are doing like Indiana Jones, like we are the archaeologists of space. And with this new James Webb, we can see very, very, very far away. And so we can investigate these galaxies at this peak of star formation. So far, so good. But let's talk more about galaxies. Galaxies, they come in different shape, different sizes, different colors. This is called the Stephan's Quintet. It's a group of 5 different galaxies. And you can see like that they look fairly different from one another. But to simplify, we classify galaxies in two groups. We have spiral galaxies, as this is the Whirlpool galaxies. In spiral galaxies, we have the spiral arms that start from the galactic center. In the galactic center, we have more stars, so it's more bright. And all these stars, they rotate in like circular motion. And also, around these spirals, you see that there's more material, there's more dust, more gas, more new stars being formed. On the other hand, we have elliptical galaxies that they look more boring, but nonetheless, we study them. These galaxies are called red and dead. It means that they don't have there is no new stars are being formed. They mostly have old stars, and these stars, they just go around randomly. They don't have much structure. So like with galaxies, they are not static, but like they are evolving environments. And what we think is that from spiral galaxy, so a spiral galaxy, it then with time, it becomes an elliptical galaxy, meaning that a galaxy which has lots of gas and therefore it forms lots of stars, somehow it arrives to the state of being like gas, depleted of gas, and so with no star formation going on. So the question is, what is the mechanism responsible for this quenching of formation of new stars in the galaxy? So how do we go from like a peak of star formation to less star formation, or from spiral galaxy to elliptical galaxies? In this image, you have a hint of the one of the possible reasons, and you can think about what this could be. But in the meantime, I can tell you that this has something to do with supermassive black holes. So you may have seen this picture from a recent movie called Interstellar, where like they fly with a spaceship near a supermassive black hole. And this is one of the best simulations we have of a black hole in movies, for sure, but also in science, because on the screenplay for this movie there was Kip Thorne, which is like a Nobel Prize for black hole physics. And also they had lots of money to produce the movie, so it was a very good simulation. But nowadays we don't only have simulations of black holes, we have real images of black hole. And you also may have already seen the first image of a black hole shadow, to be more correct. This black hole, it's in the galaxy M87. And it's located, so these very massive black holes, they are at the center of these galaxies. And this galaxy is like 55 million light years away from us, very far away. But because this black hole, it's so massive, it has like 7 billion times the mass of our sun. And this in a very small volume, so it's very compact. It releases like so much energy and light that we can observe it even from far away. And so to say more about the black hole, at the very center, we think that there is something called the singularity, which is more like theoretical concept, but you may think as the entire mass of the black hole is concentrated in a point like. A friend of mine that is has studied black hole theory, said that it's not entirely true, but somehow. We also don't understand that fully. Then you have the event horizon, And this glowing donut is basically all the matter that it gets pulled towards the black hole because its gravitational field. And going towards the black hole, it starts to spiral out. So it forms an accretion disk, which is what we see here glowing. And this image was produced by using many different telescopes around the world, using something called interferometry. So like when we want to observe something very small and compact in space, we need to have a telescope with a very large diameter, because the larger the diameter, the more we can resolve small objects. So like combining different telescopes around the world, we can simulate as we would have a telescope as big as the Earth diameter, for example. And this has been done. This is a telescope in Spain, on the North Hemisphere, and these are like two telescopes, a telescope and a series and collection of telescopes, both in Chile, in the Atacama Desert. And these data were taken in 2017, and then it took us 2 years to work on this data and analyze this data because it was very challenging to produce then and release in 2019 the black hole image. Okay. But let's go back to this image. I forgot to say that the black hole, they don't only accrete matter, they also pushed matter away with something called jets or winds. So they have, from the black hole, it's like perpendicular to the accretion disk, we have this relativistic jet that it pushes the gas away. And this is actually what we see here. We see like M87, the galaxy around the black hole for which we have the image, with its jet, which is like, you can see it's very powerful. It goes like way beyond the size of the galaxy. And this we call the active galactic nuclei, because these black holes are active. Not every black hole is accreting matter and then ejecting these so-called also outflows. Galactic because they are in the galaxy and they are like in the very center of the galaxy. And this is an artistic representation So here we have the black hole at the center, the accretion disk in yellow around it. Then we have different clouds. The clouds which are closer to the black hole, they move faster because they feel more the attractive force from the black hole. And then we have these collimated jets perpendicular to the accretion disk, and which they form like so-called lobes or bubbles. And we have also like a donut around the accretion disk, which is made of dust again. And we have a nice picture of this AGN. Like this is the Centaurus A galaxy, for example, where we can see the galaxy edge on. So this is the galaxy disk with here it's so it's darker because there are lots of dust which block us the light coming from the stars. And then we have these powerful jets with the outflows. So what I'm interested in my PhD is to understand how, if the energy and momentum coming from the black hole with these jets, it can change the properties of the galaxies. And in particular, if it can push away the gas from the galaxy. So in that way, suppressing star formation, like connecting to the galaxy before. So what I look at the central region of the galaxy, and I want to see if this, it's called feedback, it can indeed stop star formation by pushing away the gas. But to do that, I need to have something to measure how many stars are being formed. And I do that in this way. So if new stars are being formed, then they emit light, and then they give energy to a specific kind of molecules called polycyclic aromatic hydrocarbons. For their friends, just PA or PAHs. These are molecules only formed from hydrogen or carbon atoms. And these molecules, then they receive this energy from the stars, and they also re-emit the light, but at different wavelengths, so like longer wavelengths, that then I measure using the James Webb Space Telescope. And yes, and this is one of my plots where you can see, so it's complicated, but this is basically, this is the galaxy, and you see that it's brighter in the center, but also a bit far away from the center. Yeah, so I'm still, so in this case we see that in this galaxy, even if it has a black hole, we still see star formation going on in the center, but also in other places. So the black hole, it has an effect on localized, enhancing or suppressing star formation in localized part of the galaxy. And that's it. I hope if was enough clear, but you can ask me more. Thank you.
Well, thank you very much indeed for that lovely talk. Now, I'm sure we may have a few questions. For those of you who are on Zoom, if you have a question, please type it into the chat. But we've got time just for a few questions, so we'll start over here.
So are you looking at your picture of the revelistic jet and the rotating stars and everything else? Actually reminded me, Rick, because I was recently reading books on electromagnetics, and what it actually reminded me of was the right and left hand rule. Is there anything similar to that working where the force is actually forcing the things out? So it's actually similar to a right hand rule in electromagnetics?
So I'm not sure I understand what is the electromagnetic.
You get a motion caused by something crossing a field. So you get a motion of a field and it creates a force.
Ah, yeah.
So
Okay.
like solenoids work.
Yeah, no, okay, no, I know. Okay, I got it. So especially, yeah, it's a super relevant question because especially near the black holes, we have very strong magnetic fields generating from the black hole, and we think that the jets, so this black hole, we think that they have like an helix structure. So then all the charged particles, they follow the magnetic field lines, and they also like are accelerated by the magnetic field lines. And these magnetic fields, they are very, so because of this structure, they keep the particles very collimated, and that's why they're also so powerful, because they are so collimated. So it's definitely, yes, I mean, complicated, but...
It's the mechanism, but it seems to be a similar mechanism.
Yeah, no, definitely. And I think also depending on different models of black hole, from the theory point of view, you can have different magnetic field shape generating from the black hole, if it's rotating, if it's not rotating, and so on. So it's, yeah, interesting, yeah.
Thank you for that question. Some other questions? Yeah.
Simple question. you showed a picture of M55, and with your LED device, you indicated the rotation. Is there any science behind working out whether we're watching a galaxy in an anti-clockwise or clockwise rotation?
Yeah, so we can figure it out whether the stars are rotating clockwise or anti-clockwise. Yeah, by measuring like the light coming from stars and all the astrometry and the proper motion of the stars. And I don't know if it was your question, but if the spiral galaxy, they go, how they are like how this spiral it's not necessarily that the stars are going where the spirals, it sometimes is also the opposite way. So I think we have 50-50 rotating like clockwise and anti-clockwise. Yeah.
Good answer.
That's what I know.
Sorry about it, because this question's still sort of forming in my head. The galaxies are about 100,000 light years across. The Milky Way is, I think, 100,000 light years in diameter. The black hole at the centre, while it's several billion solar masses, isn't that big compared to the galaxy. So I'm wondering how the black hole at the centre is clearing out dust from the outer regions of the galaxy. I mean, how much dust is thrown out by the black hole to actually affect the formation of stars? Does that question make sense?
No, it makes total sense. It could be like the summary of my PhD. Yeah. So like you can think of if this room is a galaxy, then the size of the black hole would be my nail on, so it's very, very small. But because it's so compact, because it's so dense, like the most dense object, then it releases like an enormous amount of energy. There are some black holes for like quasars, they're called, that the luminosity coming from like the accretion disk and it completely outshines the entire galaxy. So you see only the emission triggered by the black hole, and you don't see anymore the galaxy in a way. And also because so this outflow that they come from the black hole, the gas and dust is the material that is most affected by this like pressure caused by the emission of light from the black hole. And so that's they're also they are as wide as the entire galaxy, so they reach until the edge of the galaxy, and so that's why they can push the gas really on a very long spatial scale. Yeah.
Okay, I think we've got time for just about one more question. Do we have any on the internet? Nothing on there. You waving your arms first.
Thank you. You've got two ways of seeing black holes. Either you do it visually, as it were, or you use radio telescope. I noticed when you put your photo, your slide up, there were lots. It was all radio telescopes,
Yes,
not
yes.
So you do the two together, or is it basically just the radio telescopes, or just the optical, or do you do a mixture?
I think so. The image, this was taken using radio telescope. So we, from what I know, we have to use radio waves to measure black holes. So this is the, yes. Yeah, yeah. The radio waves, they are like those waves that can peak mostly through all the material that is like between us and the black hole. And there may be other reasons for sure. But we have also other ways to know, to measure, to see a black hole indirectly. And we did that for the black hole at the center of our own galaxy. So for that, we measured the movement of stars, which are super close to the black hole. And we noticed that these stars, they were orbiting around an invisible object. And also the orbits were very fast and weird. They were not following the rotation of the galaxy. So from measuring and monitoring these orbits of these stars through a long period of time, then we were able to say that there is a black hole at the center of our galaxy. Yeah, yeah.
Okay, well, thank you very much indeed for a really fantastic talk there. Thank you. I know they take a long time to prepare.
Thank you. It was, yeah.
I'm sure we all want to say a very big thank you to Camilla.
Thank you, thank you, thank you.
When we observe it, we essentially see the star and then you can see the disk. So it's quite useful because if anything's transiting or going in front of the star, we can observe it quite well. And there were 2 planets confirmed, about 9 to 11 times the size of Jupiter, called Beta Pictoris B and C. I've not understood why there's no Beta Pictoris A, but that's a different conversation. Okay, but why is it such a cool system, to me at least? Like I said, it's a very early forming planetary system, so we're trying to understand what's happening early on in loads of planetary systems. And it was the first system we've ever found to have comets on beyond our own solar system, which was a great big deal. As you can imagine, they're really hard to find as well because they're so small in comparison to, say, a planet around another star. And so far, using spectroscopy methods, there have been 2 types of comets that were found in Beta Pictoris. There's still a lot of research going behind it because no one fully understands a lot about it, but kind of old and young comets. So we can think of this similar to the 2 different categories we have of comets in our solar system, where the older ones are a bit closer to the star, so they're about 2 AU is what we think. And then you've got the young ones, which are further out. That would probably be longer period comets, similar to the ones coming from maybe the Oort cloud. But it will be in comparison to the Beta Pictoris star, so not exactly how we see it in our solar system. And they're very similar sizes to what we see now. So most of the comets that were found on Beta Pictoris were within 3 to 14 kilometers. So when you think about 3 to 14 kilometers, it is kind of crazy to think that you could spot that on a system that's nearly 500 trillion miles away from us. A bit of background to what my project actually looked at. I was using the TESS telescope, which is a satellite in space. And new data had come out in the time that I was doing my project. And it was the highest cadence data, so like the most intervaled image of Beta Pictoris we had ever gotten before. And previously, TESS has been the main telescope that people have used to find comets on using photometry. So I was hoping to find something new in the Sector 87 data, but if I did, I guess you'd find out in a few slides. And then I worked on removing pulsation signals, so I'll talk a bit about this in a minute, but to look for these exocomet transits. So some of you might be familiar with planets. When you're trying to find planets, we use something as a transit method. If you're not familiar with it, it's okay. I'm going to have a GIF that shows it in a second. And then another part of my project, it was kind of split, was to look at what limitations we have using ground-based telescopes to observe the pulsations and to see if we can find any comets using ground-based telescopes. I couldn't, spoiler alert. Okay, so what I've been talking about is the pulsation of Beta Pictoris. So what this is essentially the star's interiors are causing kind of this effect on the outside where you're seeing a brightening and dimming factor. And depending on what type of variable star it is, you'll see different types of pulsations. For this specific, for background, you can also think of how we study this as the music of stars, is what it's sometimes known as. And you can kind of imagine it if you had like a pipe, if you were like playing an instrument, for example, it kind of creates waves, sound waves. So similarly, we're studying what's happening on the inside, depending on what we see, if that makes sense, or what you would hear. And over here and there are something known as light curves, and this is a main form of data I use now and use at that point, which is essentially you have the telescope pointing at the star and you take loads and loads of pictures of it and you measure the total amount of light coming from it at any given point. So all of those red tiny dots over there are the brightness of the star at a certain point. So you can see it looks kind of like a sound wave, you could say. And then based on that light curve, you can take out how quickly these changes are happening in it, so the frequency at which the wave is kind of pulsating, you could say. So this is what TESS data normally looks like. This was my data. This was the 20-second, so every 20 seconds a picture was taken. And you can see in the back are the blue dots, that's the actual data. And on top, red is the frequencies or the how quickly the star, again, was changing brightness over a period of time. So that's taken from this graph over here. So you've got frequency, and then you've got how strongly it was showing on the graph. So all the ones in green were the ones that were fitted on there. So you can see this star has loads of different frequencies that are happening inside of it, which is important to us later on because we want to see what's happening beyond just these pulsations. And they tend to be quite low amplitude, but very high frequency. So they'll be on the order of maybe like minutes to less than a day sort of time frame. And this star specifically had about 54 happening at the same time, or periodically. Okay. Why do I care about the light curves? This is how we actually detect the exocomets in the method I'm going to talk about. So I'm going to start with showing you this over here. So has anyone seen graphs like this if you've looked at exoplanets before? Yeah. Okay. So the basic concept, if anyone doesn't know, is as a planet goes in front of the star, the total amount of light that's coming from the star decreases. So when we're taking pictures of the star, you see a sudden dip in the brightness of it. And for planets specifically, you normally see it quite symmetrical. It'll kind of have a steep kind of drop, goes across, and then comes back up once the planet's gone across. So a similar way we look at planets, we look for exocomets. So on the top of there was a light curve to what I showed you before, similar. But underneath, once they've gotten rid of all of those pulsations that they know are part of the star, you can get out a signal like this. And this, the blue is not coming up very properly, but that over there is what an exocomet signal will typically look like. So unlike a planet where it's symmetrical, for an exocomet you'd see the head, kind of the steep decrease down there, and then a gradual increase back if you think of like the tail of the comet. So that's the distinct shape we look to find these exocomets. But yeah, so it's a lot harder because, again, signals are very small in comparison to what you see with planets. Okay, I'll break this down, but this is sector 6 of TESS, so this was about 2018, when this was one of the first comet signals they found and one of the biggest ones they found. So like I was saying, it has that steep kind of dip in the light curve, and then it gradually increases back up. So that was a confirmed comet. This was a slightly more dodgy version of what I thought was in sector 87. So this was the new data. It was a similar method of fitting it, which if you're interested, I can tell a bit more about. But you can see there's kind of that massive, I might actually use the laser for this. How do you? It's just a button. You can see that over there, there's a massive kind of gap in the data. And that's kind of crucial because I can't really see what the rest of the shape is going to look like. But roughly fitting it using similar methods, you can obviously see there's a lot of issues with the fit. You get a similar sort of velocity, and there were other parameters as well that kind of indicated that if this was an exocomet, it'd be coming from a similar place as this one. So these were coming from what I said around this 2 astronomical units around the star, and this is probably caused by Beta Pictoris b, which is around 2.7 astronomical units, causing perturbations and like kind of like pushing these comets towards the main star So is it actually an exocomet? Now, that over there is what I just showed you on the previous slide. And if anyone can notice the massive gap straight after that, so that time period is called the TESS downlink time. Now, this is the time every sector, which is 27 days of TESS, it turns towards the Earth, sends us the data, at which point the telescope shuts off, so you don't get any data during this time period, which means anything around there might be slightly, maybe noise, maybe just artifacts from the telescope. So it can be taken with a pinch of salt. So that's a main limitation on whether that was or wasn't an exocomet. I mean, the promising thing was the fact that the parameters were similar to the other one I showed you in Sector 6, but that could also just be because of the way I fit it. But yeah, that's kind of, unfortunately, hard to tell without further analysis, but unlikely not. So another way we could tell whether it was actually a comet was if we looked at stars around and saw if all of those other stars had the same sort of dip at the same time periods. If it is, then it probably is something to do with the TESS telescope. If it isn't, maybe we have some more time to look at it. But I was very limited on time, so this was my conclusion. And then going back to a bit about the remote observations I did with the telescope in Australia. So this is a light curve I took. I'll show you the light curve again from the previous slides to remind you of what it should actually look like if you were to use a telescope in space. Something like that. So this was it was observed at the exact same time as TESS was taking its data, so between December of 2024 and January of 2025. And by some miracle, I found one of those 54 frequencies at which the star was pulsating at. And a big limitation of this is weather, as I know most of you probably have experienced this before, and amount of time you actually have on a telescope. So you can see loads of gaps in data. You can see, if you want to know a bit more about the errors, I can talk about it, but I won't talk about it now. And these comets are so small and so kind of hard to see that to see from a ground-based telescope is really hard. But there have been telescopes that have been successful at looking at more than one pulsation coming from the star. And this was a telescope in Antarctica, which had the 6 months of darkness where it was just pointed at the star. So it got loads and loads of data. And also the fact that we don't really fully understand what's happening around Beta Pictoris, so we don't know when we're looking for these comets. So kind of talking a bit about the improvements and where this could actually go. The main kind of one is a very common word that's kind of used around now is machine learning. And the full concept of essentially we've got some signals from TESS previously found and seeing whether we can apply that to search for signals over and over again, but we have very few. And then we also just want to keep looking for more exocomets to build a larger sample of what's happening around. So once we build a bigger picture of where exactly these are coming from. And I think TESS has found only about 30 of Beta Pictoris exocomets, so a bit harder to place. And then this is more exciting, is long-term observations from the Plato telescope, which I believe should be in 2026, but I might be wrong. And this is going to be hopefully looking at Beta Pictoris for 12 months at a time. So if any signals were to be found, it'll be more likely to find it. In fact, instead of TESS, which is only looking at it for 27 days at a time. And spectroscopy also has been used to find exocomets, but I've mainly focused on photometry. And then I just want to end on this because this is what so the person over there, I'm not going to try to say their name because it's French, is a person who actually found these comets from TESS and said that if you were on the planet orbiting this Beta Pictoris, so either Beta Pictoris B or C, take your pick, you'd be able to see a comet every 2 days as bright as the one I showed you earlier, which was the Hale-Bopp comet. So it'd be really cool to see it. It's just about actually looking at telescopes now that can do anything to help us. But yeah, I hope that gives you a tour of Beta Pictoris system, and I hope you find it interesting.
I'm sure you'll agree that was a really terrific talk, wasn't it? So very many thanks to Anushka. So do we have some questions? I'm sure we must have.
Hello there. On the basis you said that Beta Pictoris was similar to the Sun but a lot younger, is one query being that the Earth would, if the Earth, we went on the Earth in 25 million years after the Sun was formed, there would be as many comets as you were talking about there.
So,
i.e. that it's because it's a young system.
so I actually, like, the way I phrased it probably wasn't right. So what I meant was, when I was talking about the system, the Beta Pictoris star is what we call the host star of the system. So like the Sun hosts all the planets around it, the Beta Pictoris star hosts it around it. But in terms of comets, we do expect that that's probably what comets might have looked like early on in the system. So it's kind of, I couldn't tell you the exact spectral type and everything about that specific star right now. But I think the understanding is that it was very similar to the Sun and maybe stuff around it. But because it's 23 million years old in comparison to billions of years old, it's hard to kind of, we can't see what our solar system looked like that far back. But this is maybe what it looked like because they've got similar sort of planets around it, I guess. I hope that answers.
Any more questions? Stunned.
Oh, answer.
Yes.
I've got a bit of a, it's just actually working.
Yes.
Because I've got a hearing problem at the moment. So you might have mentioned it already, but what are the principal ways of differentiating between the transiting exocomet and the transiting planet? Is it because the water content in the comet being much larger than the planet, or what other mechanisms? You might have mentioned it, but I didn't hear.
Okay, I'll go over it again because that's a good point. I can this. So the main difference is that a planet is kind of solid, right? So once a planet goes in front of a star, it's blocking quite a bit of the light around it. So a comet in comparison is a lot smaller if you think about it. So the main differentiating factor, you could say, between the planet and the comet was the shape. So for a planet, this one doesn't show it great, but it's a very symmetrical sort of dip. So you would get like almost like a U-shaped if you think about it. Whereas a comet would look a bit more asymmetrical in shape, where you've got a steep sort of decrease to begin with, and then after it's past like the middle, you could say it's got like this gradual increase back, so it's kind of more curved back, so it's almost like a the head and the tail. So you've got the head of the nucleus, which is more opaque, and then you've got like the tail following it, which is dust sort of thing. So that's a lot less, like a lot more transparent. So it's letting a bit more of the light through. So it's a bit more gradually increasing back, if that makes sense. Whereas that one's solid going across. But it's mainly the shape and the size difference.
Okay, thank you.
I think we got a question from their Zoom watchers.
This is from George Sello, and the question is, these are presumably very short period comets. What mass diameter are you predicting could be detected with this technique?
Of the comets? So I think it's about 3 to 14 kilometers is how big we think the comets are in size.
Okay.
So very, very small.
Thank you. I think we've time for one more, if anyone's got one more question. Okay. Well, I'm sure we all want to say a very big thank you to Anushka once more.
Thank you.
Thank you. Okay, that brings us to the last talk of this evening, very aptly named What's the Matter? I think we've sorted one matter out, but I'm going to pass you over now to Alessandro, who's going to give us a talk about something different. So please give a big warm welcome to Alessandro.
Thank you very much. Just like Beta Pictoris, I'm going to have my attempt B at this presentation. So yeah, as I was saying, yeah, this is a movie title. I hope you get the reference. Otherwise, I'm just going to look like a silly person. I'm Alessandro, as you can guess from my name. I'm not from the UK. I come originally from Italy, and I've done my bachelor's and master's in astronomy at the University of Groningen in the Netherlands. And now I'm here working with Chiaki Kobayashi on astrochemistry, hence the title. So in general, I would like to motivate why do we do astrochemistry? Well, to answer some of the big questions, such as what are we made of, what are things made of, and why are they made of that stuff. So this talk is divided into two parts. I'll give you a bit of background, a bit of a history of elements, of chemistry, and then I'm just going to also say where do elements come from in space specifically. What do we do here at the University of Hertfordshire? And then we're going to go into the nitty-gritty stuff of what is it that we do specifically with elements and what they tell us about the universe. So a bit of a brief history of elements in general. Elements have always been considered the smallest building blocks of anything. Since antiquity, there were already the big 9 elements, which were gold, silver, copper, iron, lead, tin, mercury, sulfur, and carbon. Nowadays, of course, we know that they're not the smallest building blocks of the universe. But at the same time, back in the day when they would extract a rock, they would try to melt it, and what would come out was always these big 9 things. So at the time, we only had 9 elements, 9 natural elements. And for practical purposes, they were more than enough. Until in the 1500s, alchemists really tried to find the philosopher's stone, the elixir of eternal life. So at some point, some curiosity got in the mix. And by boiling, for example, some fluids, for example, they started discovering new elements, such as phosphorus. And at some point, we were like, oh, wow. So if we apply heat to a rock, we're going to get one of the big 9. But then if we apply heat to a fluid, we might discover some new elements. And then chemists started thinking, what if we heat gases? What do we get out of that? And then we started discovering oxygen. We started discovering nitrogen. Eventually, they found some new techniques, such as electrolysis. And, well, nowadays, this is what we know about elements. We have up to uranium, we have all natural elements, and then we were also able to create some more elements in a lab. So there's an enormous amount of elements, and each one of these elements has a signature, has a story to tell us, basically. Also, a little bit of the history of then chemistry beyond planet Earth, because of course we weren't wondering about what stuff was made of, but in general, people just thought, with no better means, we'll just assume that every celestial body, every star, every planet, everything is just made of the same things that are here on Earth. Of course, now again, we know that that's not true, but we had no way of measuring it. And even the French philosopher Auguste Comte said in 1842 about stars, this is from French, we will never know and we will never be able to study by any mean possible the chemical composition of a star. He said that in 1842. But some people try to actually come up with a clever trick, which is, how can we extract this information out of celestial bodies? Can we extract this information from the universe? Of course, using light. So already Isaac Newton had done some experiments where if you take some white light and you have it going through a prism, you would see a beautiful continuum spectrum. But roughly 10 years after Comte said we will never be able to measure the chemistry of stars, some people actually devised a method to do that. For example, if we take the experiments of Kirchhoff and Bunsen, they took a white light, they passed it through a prism, so they repeated the experiment done by Isaac Newton, and they see this beautiful rainbow, this beautiful spectrum. Then, for example, they took some gas, they started heating that gas, and the light that would come out of that gas went through a prism, but instead of seeing the full spectrum, they just noticed that there were some lines, some kind of barcode, which is a signature of the element that gas is made of. They thought, what if we have the white light, and then we put the gas in front of the white light? We would see exactly the same image, or an image that is exactly complementary to the previous one. So in this case, the gas wouldn't emit some light, but it would absorb it. And it would absorb it in exactly the same locations that it emitted earlier in. So then we thought, can we treat a star in exactly the same way? I actually have a laser pointer. So what if a star in its nucleus has some source of energy, which at the time, of course, they didn't know just yet, which has a certain continuum, and then it has an atmosphere around it. So it has just this cloud of gas, and then the star just emits this light, it goes through the cloud of gas, and then it gets to our eyes. Then we would get an absorption spectrum like this. So a spectrum, or a rainbow if you wanted to in the optical, that is missing some light. But also in general, we have stars that have these kinds of mechanism. But also if a star is lighting up yet another cloud of gas, and we don't get the direct light from that cloud of gas, but after a while the cloud of gas cools down again and re-emits some of these wavelengths. This way we understood that we could probe both the chemistry of a star and the chemistry of some clouds of gas in the universe that are light up by those stars. It was the case in Heidelberg, Germany, when Fraunhofer started analyzing these photographic plates with spectra, and he started noticing that there were some lines missing. These were effectively the first observed absorption lines, but the way they had to work back in the day was simply, I'm going to open my window, I'm going to stick a prism there, I'm just going to have some light go through it, save this on a photographic plate, and then try and extract as much information as I can. Nowadays, we can take this light, this wavelength range of light, so this rainbow, and we can actually zoom into it an enormous amount. So this is the first time the sun was analyzed, and to date we have the best spectrum of the sun from NASA, which looks like this. This is exactly the same segment, but just at an enormous amount of resolution extra. And as you can see, in this case, there are an enormous amount of absorption lines. And each one of these absorption lines is a signature from a specific element that is telling us about some phenomenon going on, in this case in the sun, because it's the spectrum of the sun. So we started analyzing then elements coming from stars, elements coming from also faraway galaxies, and we all reconvened to the fact that hydrogen and helium, the two lightest elements, were already there after the Big Bang. The Big Bang explodes, stuff recombines, the first atoms to be there are hydrogen and elements. And they, to this day, they still make 99.999% of the baryonic matter in the universe, so the matter that we interact with. Then most of the other elements up until iron are made in the cores of stars. We discovered that the powerhouse of a star is nuclear fusion. So these lighter atoms are smashed together to form heavier and heavier elements up until we get to iron. Then from iron to literally every other natural element needs some other process. And these processes happen when a star is dying. A star is dying, its nucleus collapses, there's a big explosion, super energetic event, and a lot of these atoms, a lot of these elements that we have are smashed together, and they actually start forming heavier and heavier elements. And as I was saying before, anything heavier than uranium was actually made into a laboratory. Also, a little curiosity. I don't know if you ever noticed that there's this element here, number 43, that is called technetium. Technetium is also an element that it's extremely difficult, if any at all, to find in nature. And it's called technetium from the Greek tekne, which means the art of making something. And in this case, they made it into a lab, so it was the art of making the element number 43, just a little curiosity. However, astronomers, most astronomers, I do, but most astronomers really only care about hydrogen, helium, and everything else is metals, and iron, star killer, and then everything else is just an eject from a supernova. So if you talk to an astronomer, this is their periodic table. But then what do we do here at the University of Hertfordshire? We simulate, in our group at least, the universe, and we do cosmological simulations, so simulations that basically represent almost all the universe, if not all the universe. And what we do is we see an observation, we can't understand it, and we try to run our simulations to reproduce that specific thing, and then we explain a phenomenon, for example. Then in our simulation, we have an enormous amount of information. We extract that information and we're like, we haven't observed this yet. But is it possible that this phenomenon is happening and we just don't see it? So not only can we try and understand with our simulations how the universe works, but we can also make predictions of how we expect the universe to work. This image here is, for example, a cosmological simulation done by my colleague, my second-year colleague, Alice Ferreira, that is going to soon publish these findings. And she also studies dust in the universe, so she can track how dust evolves in the universe. In my case, I focus more on the local group, on the nearby universe. So we live in the Milky Way galaxy, and around us there are a number of dwarf galaxies. We have the Sagittarius, Sculptor, Fornax, Carina, the Magellanic Clouds. You might have heard of these galaxies already. And some people, in this case my bachelor supervisor, Elena Tolstoy, was extremely interested in dwarf galaxies because she noticed they are galaxies, but smaller. So we have no we have no expectation of them behaving any differently than a regular big galaxy. This is the assumption with no prior information, right? The universe works all the same. And then we look at the chemical composition of this dwarf galaxy, so the ratio of magnesium over iron versus iron over hydrogen. And we can see that the Milky Way, the white dots, the white squares, evolve a certain way. And there are some of these dwarf galaxies that I pointed out that populate some areas that are maybe a bit below the Milky Way. But then if the universe and the principles that regulate it are all the same, why do we see some different yields? And this can be seen, for example, in magnesium over iron, but it can also be seen in calcium over iron. So is there some sort of correlation between the two? Does this tell us something about how the galaxy evolved? Does this tell us something about how stars work? There's, as you can see, an enormous amount of information that we can extract just by looking at what stuff is made of. So this is a PDF file, unfortunately. So this was going to be what I do in this group, which is I take a cloud of gas, I put it into a dark matter potential, and I let it collapse, and I form my own galaxies, my own dwarf galaxies. So in this case, Eline, the person who wrote this paper, would come to me and would ask me, can you actually play with your simulation, and can you see if you can recreate these chemical patterns? Now, this should have been a beautiful movie of gas collapsing and forming a galaxy. You will have to trust me on that. This was also a zoom in because it was very beautiful. And yeah, so as we can see, we have two simulations that I ran with completely different parameters. And in red, you can see a much more massive galaxy, a much bigger galaxy that seems to follow a little bit the pattern of the Milky Way. So we arrive at more or less -1, and then we have this dip. We can also see that there's a certain spread here, while here everything seems to be a bit more collimated, and it seems to be the case also in our simulation. Then I take a much smaller galaxy, for example, and I add also some specific processes to it. So I add an exotic type of a supernova, and we can see that we form less stars, but at the same time we are able to recreate this dip a bit earlier that comes from dwarf galaxies. Of course, this is not a one-to-one match. I would know how to move this one here, but it just takes an enormous amount of time to run a simulation, so I wasn't able to do it in time. But for example, when we look at a picture like this galaxy compared to this galaxy has a lot less dark matter concentration. It has a lot less stars forming in it. Less stars forming means less elements. So less elements means less iron. And that is why it's, for example, moving to the left. So yeah, from elements we can extract just an enormous amount of information. And this is how I learned how to stop worrying and love the periodic table. Of course, I'm just at the beginning of my research, but this is a periodic table that was done by my supervisor. And as we can see, this is exactly the same picture that we saw before. So this is a periodic table. And each little square is a graph. From 0 to the age of the universe, we can see from 0 to 100% how much of each element formed, because of what process, and at what point in time. So we know that all of these elements have been extracted or have been generated by, as I was saying, hydrogen, helium, and actually a bit of lithium are generated by a Big Bang nucleosynthesis. Some of these elements are, for example, mostly in the universe because of the work of asymptotic giant branch stars, so a special type of stars that have winds that contain an enormous amount of these elements, as well as, though, a lot of other elements. Or you might have heard maybe at some point of core collapse supernovae, and we can see that core collapse supernovae have high quantities of magnesium, of silicon, of oxygen, for example. So I actually would like to leave you on this periodic table, and I would like to thank you very much for listening, and if you have any questions, I'll be happy to answer them. Thank you.
First of all, a very big thank you, Alessandro. What a terrific talk that was too. Thank you. So, do we have some questions from the audience? Right at the back.
So, it's just a quick question because I've seen this graph a few times previously. I haven't seen the dotted lines on it before. What are the dotted lines that are going for each of the elements?
It's where when the sun was generated, so the sun was generated 5 billion years ago roughly, and how much of each element it had when it was generated. So in this case, the sun would be here for this element, which I don't know what it is. But yeah, it would have like this much magnesium, this much sodium. So it also shows you how the sun compares to like a star that was born more or less at the same time. So the sun is a little bit underabundant in sodium, a bit overabundant in magnesium, quite overabundant in carbon apparently.
Thank you very much.
I see you've got four different types of, five different types of
Phenomena.
Element creation. Is that 5 Big Bang nucleosynthesis?
Yeah.
Is that the 25% helium and
Yeah,
the rest
yeah,
hydrogen, apart from a bit of rubbish? Okay. So which ones of those is the rapid neutron?
The rapid neutron capture usually happens in core collapse supernovae and neutron star mergers. But at the same time, I would also like to stress that, as you can see, not all elements reach 100%. Why don't they do that? The reason is because effectively, these are some of the processes, the most popular, the most famous processes that create these elements. But even if we just look at novae, so just explosions of stars, there are supernovae, and then supernovae are type 1a, type 1b, type 1c, type 2, which are core collapse supernovae actually. Then now we are also investigating the possibility of studying supernovae subchandra type 1a. We are investigating kilonovae, we're investigating, which are actually neutron star mergers. We're investigating hypernovae, we're investigating pair instability supernovae. So effectively, we cannot explain the whole of the universe via these processes. These processes are just the most common processes happening in the universe.
Okay, I think we've got a question from our Zoom audience.
It's from George Selle again. Excellent talk, thanks. Do we have any understanding on how dark matter has influenced the ratios of element production, or is our understanding that this is purely stellar synthesis independent of dark energy matter?
So dark matter, in on itself, at least for now, we don't think really interacts with baryonic matter. So there isn't a direct correlation. But dark matter effectively generates gravity. More gravity with a lot of gas generates more stars, and more stars yield more elements. So dark matter, we could probe dark matter with element formation, but it's not a one-to-one thing. There are a lot of other parameters going into it.
Okay, do we have any more questions? Yep.
Thank you for your talk. At a recent talk here, one of the speakers referred to the Sun as being a third-generation star. Now, unfortunately, I didn't get round to asking him what he meant by that. Do you understand what that means, and if so, could you explain it, please?
Yes. So the first generation of stars were all those stars that were born basically in what Camilla was showing us at cosmic dawn, basically. So the gas was just made at the time of hydrogen, helium, and lithium, just the first three elements that were generated right after the Big Bang. So the first generation of stars were effectively stars that only had these three elements inside of them. They were extremely pristine stars. Then those stars were also believed to be extremely massive and exploded quite early on. And they polluted effectively the whole of the universe with all the other elements already. There's a new generation of stars that then form with already certain amounts, from trace amounts to big amounts, of every element at this point. And they also started fusing, again, hydrogen and helium into heavier and heavier elements. And then part of that generation of stars also already exploded. So a third generation of stars is the generation of stars that has been that have inside of them gas coming from the pollution from the first generation of stars and the pollution from the second generation of stars.
Any other questions? No more on the internet? Okay, well, I would like to say a very big thank you to you, Alessandro. What a terrific talk. The amount of work you must have put into that is outstanding. So can we give Alessandro a big round of applause? That almost brings us to the end of this evening. But I would like to ask, could all the speakers come up to the front for the moment? We've got a little something for you to remember us by.
Thank you.
Thank you.
And Alessandro. As I say, you can look at that at leisure and remember your time here. I think it's been remarkable that we've learned so much about the past of astronomy, but standing by us, we've got the future of it. So a very big thank you to all of you. We wish you well in your studies, and we look forward to seeing you perhaps another time. Right, just a few announcements. The calendar. We've got a very busy time over the next few weeks, so to make sure I don't forget anything. This time next week, 18th of March, Bengio School in Hertford have got their astronomy evening. First of all, thank you to all of you who have volunteered to come along, bring a telescope along. We hope the sky will be clear, but don't worry if it isn't. I'm sure our friend Richard will be bringing his artificial planets along for us to focus on. It's a really good evening for a primary school to put on an event like this is remarkable. They've done it several years now, and I can assure you we get as much out of it as the children and their supervisors do. So that's 1 week today. Please note it actually starts at 6:30, not 6 o'clock as advertised. We did tell them that at 6 o'clock it will still be light. But then again, if we're setting up telescopes, if we got there at 6 o'clock, that would be ideal. Then on the Friday after that, it's the Bayford-Berry Observatory Open Evening. And this is the last one of the season, so if you haven't been along, now is your opportunity to come along. You can either go on the website and buy yourself a ticket, or you can bring a telescope or some of your expertise in astronomy and come along and get in for nothing. Do a little bit of time with us. John? They've sold out. So the only way you're going to get in is by volunteering to come along and help us. Thanks, John. And then on the 25th of March, Hagas, our astrophotography section, they've got Rolf Wahl Olsen coming along to talk. Well, not actually coming along. He's in New Zealand, so he's going to join us on Zoom. Now, I've been along to a couple of the recent HAGAS meetings, and I've got to tell you, they are brilliant. They're not just about astrophotography. The things which are being photographed are talked about in great detail, and it's a very enjoyable evening. So if you want to come along to another astronomy evening, not just about astrophotography, then put that date in your diary, 25th of March. Our next meeting here is on April the 8th, where we've got Sheridan Williams coming along, and he's given us a talk on fascinating astronomical facts. So I think that's going to be a really interesting one too. Our observation group are still keeping an eye on the sky. We did manage a clear night. Not many of them this season, but you know, they do come along and make that a really good evening too. If you're interested in joining that, have a little word with Alana or Richard, who are at the back of the room waving their arms about slightly. Have a word there, or you can look at your last newsletter, sign up, join up, and we'll just send you a message. The next bit I have to read out because it's about social media, and those of you who know me know that that's not one of my strengths. So if you're on Facebook or Instagram, you can follow us at Hertford Astronomy Group, all one word, to stay up to date with meetings, events, and see lots of the group's fabulous astrophotography work. Did I get that correct, Alana? Thank you. Formal notice of the AGM in May, at our May meeting on the 13th, just before Lewis Dartnell's talk. If you're interested in joining the committee, come and have a word with myself or any of the other committee members. Those of you who are not really turned on by AGMs, if I let you know that 10 minutes is about as long as we spend on them, unless anyone's got anything controversial, in which case you can come the next night and bring it up to whoever's here. So that's the end of it. A very big thank you to our speakers this evening, and to Ben Birmingham and his team up at Bayfordbury Observatory, who look after us. We're really pleased to have that strong association, and for organising the talk. We really think that was fabulous of you tonight. So to all of you, thank you very much indeed for coming along. To our teams who are working behind the scenes like mad to keep the pictures going, the letters coming out, the notifications flowing, I'd like to say a big thank you to you. And of course, to the audience for coming along. Have a safe journey, and we look forward to seeing you at one of our future meetings. Thank you and good night.